Welcome, those of you joining us for this session of Shadow the Scientist, getting ready for a CFHT Eyes on the Sky from the Waimea control room. My name is Jamika Marshall, and I am the Shadow the Scientist Programs Manager, your session host and moderator. Our guest scientists for this session are Virja Katu, Alexis Acohido, and Lisa Wells. You are certainly in for a treat always with this incredible CFHT group. Let's start off with our main guide for this session, Dr. Virja Katu. Virja, welcome. Thank you for having us.
Thank you so much, Jamika, for that lovely introduction. And hello, everyone. I am Dr. Virja Khatu. I am a resident astronomer at the Canada-France-Hawai'i Telescope, CFHT. Tonight we have Alexis Acohido. She is one of our remote observers. She is in charge of the control room and doing the observations tonight. But we also have another remote observer to help us out with the event. So that's Lisa Wells. They both are right now sitting in the control room at the headquarters, which is in the town of Waimea on the Big Island of Hawaii. And I am actually joining from home. I am also in Waimea, but I'm at home right now. So welcome everyone to the CFHT Shadow the Scientist session. And we will check in with Alexis if we are good to open. And if yes, I can share my screen.
Yeah, so go ahead, Veronica, share your screen. I was just waiting a little bit to get the session started, but we're right at the right time for us to open our shutter, so I thought that would be kind of a fun thing to share with you all.
Sounds good. So this is the inside of the dome of CFHT, which is observatory on the top of Maunakea at the summit. So there are cameras inside the dome that show us different views of what's happening inside. And this is where we are right now seeing the floor, which is just beneath the telescope. Alexis will go through like what kind of checks and stuff she does before starting up the night, before opening the dome. So Alexis, can you talk a little bit about that as we see the opening?
I did put the windscreen up. Yes. So it's a little windy right now. Between like 15 and 20 knots is when we start to think about using our windscreen. So that's just that lower kind of panels that you see in the video right now. And right now our shutter is opening as well. So things that we're looking for, like right now humidity is a little bit high, but it is well below our limits. Other things that we're looking for are if there are summit level clouds and fog. Last night we even had some fog, so we did have to close up during the night. Yeah, and so conditions are looking pretty okay for right now. Hopefully they hold as the sun sets and we're able to get some good data tonight.
That sounds great. So you can see in the picture over there, there is the shutter that is slowly opening up. It's very slow, so it's gonna
it takes about 6 minutes to do the whole thing.
So is this what we're seeing in the top image? Yeah.
Yes. Over here, right over here.
Oh, wow. Okay. Yes. And for those of you, I see a few of you have just joined us again. Welcome. Oh, someone else just joined us. So I'll start again. Again, welcome to this session of Shadow the Scientist. We've just gotten started here with Dr. Virja Katu of the Canada-France-Hawai'i Telescope, along with her colleagues, Alexis Acohido and Lisa Wells. Alexis is actually running the telescope right now. We're looking at the dome slit opening. Is that right, Virja?
Yes, it's the shutter. We call it the shutter. And we are opening the shutter because that is the part from where the telescope will be able to look at the night sky. And as we want to see different objects in the night sky in different directions, we basically rotate the dome so that we have that opening in different directions and also rotate the telescope along with it so that we are able to point and observe in different directions. So right now the shutter is opening up. It's slow motion. We spoke about it. It takes approximately 6 minutes to open up, and it opens up from the horizon, like halfway up to 90 degrees. That is how much it opens up, roughly.
Liz, you just asked a question about how does the weather in Hilo affect us. Because of the height of the mountain, we're almost at 14,000 feet. And because we're that high, we're above the inversion layer most of the time. So the inversion and any clouds that may come in and rain on Hilo are going to remain below the mountain. So just wanted to answer your question real quick.
And I believe Viraja will probably go over, like the shape of Maunakea and what the inversion layer actually is as well.
Yes. Once we finish up once we actually watch the opening, I'll move on to talking a little bit more about Maunakea and stuff.
They just looked
So can you speak a little bit to in which direction the dome is in which direction the shutter is facing right now, and why is it in that direction?
So right now our park position is to the north usually. Because the hurricane is coming, it might, we might rotate it to 90 to 100 degrees or something like that. We usually park it north, just because it's kind of out of the way of the other telescopes. So if we have to turn on the lights for whatever reason, the lights are on right now as we're opening the shutter. It's not affecting any of the other telescopes.
Yeah, and you can see in the bottom pictures over here, you can see the dome lights, they're still on. As the shutter is opening up, you are slowly able to see the instrument which is mounted on the top of the telescope. It's not yet so clearly visible. Maybe it's like clearly visible in this picture right over here. So that is the instrument that is with which we will be observing tonight, and that's called MegaCam. It's a wide field camera, meaning that it observes a very wide patch of sky, 1 degree by 1 degree. And that is an imaging instrument. So basically it takes images of the night sky in different colors, in green, red, blue, depending upon whichever colors are requested. So it sits right at the top of the telescope. If I can, oh no, I cannot move that. Just trying to figure out which would be a good picture, but we are seeing the shutter opening right now, so it's good.
So now on the summit at this time, are the other observatories also preparing to open?
Sure.
Yes.
Yeah, most of them probably are. Some of the bigger observatories don't necessarily open their shutters until right when the sun sets. What time is sunset right now?
Sunset is about 7 o'clock.
7 o'clock right
Yeah.
now. So they may wait for another hour before they open, since it's a little early still, but they're definitely checking out the weather up there and probably getting set for the night as well.
Yes. With the incoming hurricane, there are a couple that are not going to be open from now until, Monday.
It passes, yeah.
Yeah. Usually we'll open our shutter and our vents, and that's just to flush out the dome, try to equalize the temperature and not have as much of that like thermal difference. And now actually I can go ahead and open the mirror covers. So if Viraja, you wanna, yeah.
Yep.
Switch it over.
So these are the mirror covers. The mirror is in a circular shape, but it has a hole in between. So that is the hole that you're seeing right over here. All the dark gray petal structure, that's actually the cover of the mirror. So as we are opening the mirror, it's basically the petals open up and they open up in an alternating fashion. So there's one set of petals that open up, and then there is another set of petal that opens up.
So as we're watching this experience, I just like to again thank everyone who's joined us right now. We have the Hilo Stargazers, Liz. We have Gregory, also Julius. And I did ask everyone where they're joining us from. So Liz is joining us from Hilo, the Hilo Stargazers. Julius is joining us from Nigeria. So he's an astrophysicist. He's completed his master's in astrophysics, but actually never had an opportunity to experience hands-on observing. You're in the right place, Julius. You're in the right place. Uh, yes, we have Rob joining us again, one of our um, stalwart supporters. Thank you, Rob, for being here. Always fantastic to have you. And oh, that looks almost completely open.
Yes, it is. It is completely open, where you can see in the mirror, you can see the reflection even of the petals and all the structure which is up there. You can see the reflection of that in the mirror.
Oh, you sure can. I see that now. Oh, I see that now.
Yeah, yeah. This is all the thing from the top that you can see, and there's the petals that you can see the reflection of that.
Think I'm deciding to leave the vents closed for now. It's a little windy, plus the vent temperatures are a little bit low. And so we have different thresholds, different limits for certain systems. And for the vents, we're kind of skirting that edge a little bit, because I'm anticipating not so great weather tonight. I'm just going to leave it closed for now. I'll reassess a little bit later, closer to sunset.
Yeah, so those are our vents that if we need, we can keep them open.
So there are multiple cameras that we're looking through here for these spectacular views, right now. Ah, yes, yes. Now,
This is
could
a
you?
great view.
This is. I was going to ask you to tell us about this view. I love it.
Sure. So the telescope is still pointing straight up. This is, I believe, that's the windscreen. Lisa, is that correct?
Yeah, that's the windscreen right there. We're
Yeah.
up about 5.5 panels right now.
Yeah, so that's basically to control the speed of the wind. Right now, what's like the wind speed is, it's kind of fluctuating.
Just under 25 knots, I'd say.
Okay, okay. So yeah, so that's for safety. The telescope, we can see a full picture of it, I think, over here. Okay, so that's actually a full picture of the telescope. The MegaCam instrument that we saw earlier that was on the top over here. This is a different instrument, but the MegaCam is also mounted the same way. That's the entire, like the tube of the telescope. The mirror is right over here where we saw it opening. So that's like enclosed in this area. And down over here, there are all the spectral instruments. So the instruments that actually measure spectrum. So that's basically a dispersion of wavelengths. When we see light at different energies, those are the instruments that measure that light. The imaging instruments, those ones that only take images, those are mounted right on the top. We call it prime focus. And all of the ones that measure the spectra, they are mounted on the bottom, and we call that Cassegrain point of the telescope. So what we are seeing over here, so that was the bottom part that we were seeing, where we generally have the spectral instruments. That is where the mirror is, sort of, roughly. That's the entire tube, which is kind of like hidden behind. And that's the view that we have right now in this picture.
So what I'm going to do right now is I'll move the telescope first. We'll watch that.
Okay.
We'll usually point it point the telescope and the dome slit to the east while we're waiting for the sun to set. This is to just completely be out of the way of the sun. And again, to just like get that temperature differential equalized. Sure. Let's go ahead and move the telescope. Fire it up.
I always love the sound effects. Alexis, the sound effects are great. So, in case in case someone's never heard these sounds, Elisa, can you tell us about the sounds we're hearing? These buzzing sounds and different things. What is going on?
Yeah, absolutely. It's actually a fake sound that's coming through the computer, but that it was engineered so that it would let us know kind of how fast the telescope was moving. So the higher the pitch, the faster the telescope is moving. So when we're slowing, it goes to its highest pitch. And as it's slowing down, you'll hear it kind of ramp down a little bit as it gets into position. And it works for both the RA and DEC as we're moving the telescope. So.
Okay, so we have our telescope in position, and now we're going to rotate the dome. And these sounds are actually playing at the summit.
Yeah.
So, yeah, we're listening to those. It's good for us to keep the sounds on just so that we can hear during the night, just in case, you know, things fall, things sound crunchy that aren't supposed to sound crunchy.
Yeah.
And so we can make note of that, call people that need to be called. Yeah.
Yeah, so the audio control for the sounds, it's inside the control room where the ROs are sitting right now, where the observers are sitting. So they're able to control the level of the sound so that if they can hear it much clearly. And you can see in the picture over here, we can see it appears as if the floor is moving, but it's the dome that's moving.
Yeah. So that particular camera is actually mounted on the dome itself. So it looks like the floor is moving instead of the dome itself, but it's actually the dome that's moving. So
It's quite disorienting.
it can be. Actually, if you're standing on the dome, you can sense the motion, but sometimes you feel like, oh gosh, it's the rest of the building that's rotating and not me. So yeah, it's interesting.
Yes.
Yeah, it's a little bit better in this picture. You can actually see the dome moving.
So we also have this little Pac-Man, and what it does is it shows us where the dome slit is pointed and where the telescope is also pointed. And so we want to watch that during the night to make sure that the telescope is always looking out the slit when we're actually doing observations, because we don't want the dome vignetting or covering part of the field. So.
Yeah, and so right now we're good to go. We're in position, and so we're just waiting until a little bit closer to sunset, and then I'll start taking flats around then. Yeah, so about 40 minutes. Yeah.
Sounds good. So while we wait for that, would like to just get us oriented where we are. So if we look at the map right over here, let me switch to terrain. We are in Waimea, so that's the town of Waimea in the north. The telescope itself is on Maunakea, which is the top of the mountain. So you can see the topography. The mountain is at the summit is at 14,000 feet above the sea level. So much higher than the actual town where we are sitting right now. The light pollution. This is light pollution map. And you can see the light pollution is much less in the Pacific Ocean. So if you look at these are the Hawaiian islands. So there is some light pollution on the islands, but if you look at the big island of Hawaii, specifically where we have the mountain, light pollution is much lower than down in the cities where there is Kona and Hilo. That's where there is most of the light coming from. So on top of the mountain, where we are already about a lot of atmosphere, there is not much light. pollution that reaches the telescope. So we are kind of in this zone in this dark dark sky area where we are able to observe nicely. This is one view of Mauna Kea from the Hilo Bay. I really, really love this picture, so I want to share it. It is snow-capped Mauna Kea. You can see very nicely, and we are all the way at the bottom of the hill. This is one picture that shows a very steady looking air on top of Mauna Kea. So the part that Alexis was mentioning earlier as to why Mauna Kea is so great in terms of observing the night sky is because because Mauna Kea is a shield volcano, and what that means is the airflow on top of Mauna Kea is laminar. So it has a very steady flow versus a turbulent flow. A turbulent flow is when air is churning, like the warm and the cool air, they're mixing up, and that causes a lot of turbulence in the atmosphere, which is not good for observing nighttime sky. So having a laminar flow is it's a very steady flow of air, and that reduces a lot of that turbulence. So Mauna Kea is one of the best sites in the world where we can do astronomy. So that is a little bit about Mauna Kea in general. This is the observatory, CFHT, as it looks from outside. And again, you can see the observatories are like on the top. You can see the cloud layer is little below the level of the observatory. So it's not, the clouds are not actually hindering our view. This is when the vents, you can see these are the vents that are open. This is the dome shutter that we saw, the opening of the dome shutter earlier. And before we move on to like talking about the science part, I would like to send it back to the control room. Can you guys talk a little bit about the things that you make sure all are safe in terms of like safety and in terms of weather? What are the checks that you do before beginning the night? So before making the decision that it's safe to observe and safe to open for the night.
I did also see we had a question in the chat.
Okay.
Yes, I'll get to that question. Please go ahead and answer that first, and then we'll get to that. Thank you for noticing, Alexis.
Yeah. Just didn't want to miss it. So yeah, so some of the things that we look at for when we're opening is, of course, wind speeds, humidity, and also things like particle counts from the volcano. So, and this was actually relevant last night. We had an episode of volcanic fountain coming from Kilauea, and it was actually so big and so bright that it kind of lit up some of the webcams. So that was pretty cool. But when it goes off, it has a tendency to let off a lot of fog. And so, you know, a few years ago during the Mauna Loa eruption, we were noticing that we were getting some particulates coming up to the summit, and some of the gases being let off by the volcano, like sulfur dioxide, if it mixes with the ambient humidity in the air, it can create sulfuric acid, which is very, very, very bad for our mirror coating. So last night we did actually have some pretty thick fog up at the summit. So we were closed for the latter half of the night. But yeah, things like that are things that we're watching out for. We're constantly monitoring during the night. And if any of these get above our threshold, then, you know, those are grounds for closing. So right now, humidity is at about almost 65%. At around 80-85%, that's usually when we'll close, depending on what it looks like outside. Sometimes it is a little bit humid, but the skies are really clear and there's no like threatening clouds. And so that's usually when it comes down to our experience as remote observers, to be able to say like, no, I'm pretty comfortable pushing it a little bit, maybe to like, you know, 90%, things like that. Wind is also a huge factor. So like you saw, I had the windscreen raised even before we opened the shutter. And I'm choosing to keep the vents closed because it's a little bit windy and temperatures are a little low. And with the hurricane coming, you know, we are expecting some pretty strong winds. Subaru telescope, actually, there was a hurricane, what, like a year or two ago, something like that, where the winds were so strong that it actually sandblasted the side of the Subaru telescope. So it is actually a little like brown, took off the paint. So yeah, these are all things that we're watching out for during the night.
And that's why we do have an evacuation limit as well when we're up there, and especially during the day when our day crew is up there. If the wind gets up above about 55 to 60 knots, which is about 65 miles per hour, they have to leave the summit. And part of that is because not only will the car get rocked a little bit, but it will sandblast the paint off the vehicles as well. And so we want to make sure, and it will hurt you as you're walking outside. And if it gets higher, if you get a higher gust than that, it could even knock you down. And so we want to get people off the mountain when the wind is really, really high up there.
Yeah. And also to mention, there are a few telescopes that still have people up there during the night, and we do talk to them. We're all on a Slack channel together, and it's just to help each other watch out for conditions during the night. And in fact, one of the Subaru operators last night was the first one to notice that we had some fog coming down. So
Perfect.
kudos to
I see
Sean.
you're on the webcam page. I've actually have that link right there in the chat, and I actually was just about to show a live view of the summit. So I'm going to do that. Okay, and so this is a live view of the summit. This is from the Subaru telescope. Actually, Alexis was just talking about Subaru. This is one of their live cameras facing east, and of course, those two domes closest to us are the Keck telescopes. And then here, kind of at the front, you have the NASA Infrared Telescope Facility. This dome here. Then you have Canada-France-Hawai'i telescope. There you are, right here, this dome. And then to the right is this is Gemini North. So this is facing east, and it is a beautiful, beautiful start to the evening right now. Beautiful start to the evening. But I know you do have to wait a while, regardless of weather, before you can actually get on sky. So maybe Virja, Alexis, Lisa, maybe talk to us about the 18-degree point of the sun and why that is so important.
You want to go?
So we actually take sky flats. So we have to take sky flats. And as soon as the sun is gone from the sky, we can start taking sky flats. And even before in the infrared, we can do that. But that is to get rid of pixel to pixel variations in our images. So we use those to reduce the images later. But at the 12-degree, depending upon which instrument is on our telescope, we either start observing at 8-degree twilight or 12-degree twilight.
Okay,
and
12.
At 8-degree, we can start with our infrared instruments. At 12-degree is usually when we start with our optical instruments. And that just means that the sky is dark enough that we won't have high background when we take our images. We want the sky to be a certain darkness. And so when we talk about 8-degree or 12-degree, that's how far the sun is below the horizon for us. So at 18-degree below the horizon, that's when we start some of our major high profile projects that are doing major surveys in the sky. They request that it be dark enough that they don't have the sky changing very rapidly as the sun is getting lower and lower below the horizon. So at 18-degree is typically where a lot of our high priority projects are starting. So.
Brilliant. Thank
For
you,
MegaCam,
Lisa.
For
Sure.
MegaCam, we start science at 12-degree below the horizon.
Yeah.
For MegaCam, okay.
Yeah.
MegaCam, yes.
And we'll be doing flats from sunset until about almost 12-degree. So.
And once we start taking the flats, we can start taking a look at those flats and how they look like.
Oh, nice. Okay, maybe we can we see those flats? Can we be a
not
part
For
of that?
sure. For sure. I'll start flats in about half an hour.
Yes.
Okay, perfect. In the meantime, let me get back to the questions here we have in the chat. First, I'd like to welcome, we have some other people joined us. Michael of the Kona Stargazers, welcome, welcome, welcome. So keep on sharing with us in the chat where you're joining us from. Questions, comments right there anytime. So Julius asked a question and Rob has answered it, but I want you all to have the opportunity to do so as well. So Julius says he's curious as to why the shutter is a common tradition seen on most domes. Won't the shutter get in the way of the camera capturing and capturing computing angle or capturing angle, I think, or will the camera be lifted above the dome to get a larger angle of view of the sky? Now, Rob says, Julius, the view through a telescope is usually pretty narrow, usually less than a degree. So the shutter opening is more than enough for that. Virja, Alexis, Lisa, would you like to add anything to that response?
Yeah, that's true. So yeah, the field of view that we're looking at is usually, much smaller than the shutter itself. So we have more than enough clearance to look through the shutter. Also, as we're moving the telescope throughout the night, we can put it in what we call automatic mode so that the telescope and the dome shutter move in concert with each other. So like as the telescope moves, the shutter is moving with it so that the shutter is, or the dome is never occulting the telescope, is never occulting our field of view.
Yeah, that's when we say that the telescope and dome, they're in the tracking mode. Is that right?
Yes. Yeah.
That's when we say they're in the tracking mode, and they both follow, the telescope is following the dome. Is that right?
I believe so. Yeah.
Okay, yeah.
Okay, yes, we're going to go with that. The telescope, it's trying to move the dome. We're going to say yes to that one. Absolutely, absolutely. Okay, so thank you, Julius. Follow-up questions, please let us know. Thank you, Rob, also for the response. Okay, so now I'm showing here one of the beautiful views of CFHT. This is on the Maunakea Observatory's website, Maunakea Weather Center. I dropped a link there in the chat, and Alexis, or I'm not sure, Alexis, maybe it was Virja, was showing the Maunakea Weather Center earlier. This is a great view, CFHT webcam images, all of them are nice. CFHTs are great right here. So do check those out. So I'm going to stop sharing here because there's definitely a lot that goes on at this time of the evening, and Alexis and Lisa have already been talking to us about this. We know that Alexis is going to start dome flats in about 30 minutes, 25 minutes or so. But in the meantime, maybe Alexis and Lisa, could you tell us a little bit more about your roles? Do there need to be two of you in the control room? Because I know at some observatories, like Gemini, there are two different roles, so you need to have two people. And since Julius hasn't actually had any hands-on observing experience, maybe you could share insights with us that Julius could also benefit from too, especially if you're trying to put that master's degree in astrophysics to work, Julius. Yes, Alexis, Lisa.
Yeah, so we are remote operators.
She's gonna do it.
Usually it's just one of us tonight. I'm lucky enough to have Lisa right here for Shadow the Scientist to help me out. But once this is over, Lisa will go home and it'll just be me tonight. We at CFHT and most telescopes now work through what's called Q observing. And so classical observing is, an astronomer will send us their proposal and then they'll actually come out here to observe with us. That doesn't usually happen. Every once in a while when we have special projects, they will. But generally speaking, it's just us during the night. Yeah, so Q service observing is a little bit more convenient for the astronomers as well. In classical observing, they send us their proposal, they come out here. Well, what if they get weathered out, like probably tomorrow or something like that? too bad, so sad, apply again next semester. And that sucks, right? Like you don't want to wait another 6 months to a year to try and observe your project. And so with Q service observing, they'll send us their proposals and also the conditions, the type of conditions that their program can handle, whether it be, you know, maybe a little bit softer seeing, maybe it can handle a little bit of clouds and some extinction, or maybe they need like really, really crisp, clear skies during the night. And so we as operators, when we're given those constraints, can make sure that we're observing the highest quality science that we can, given the conditions of the night and given the time of the year. So much better for us, much better for the astronomers that we're collecting data for.
Yeah, and they can save their money now for page charges for their papers and for conferences when they go to present their data. So they can just pull the images back home through the web now, and they don't have to travel here again unless they want a nice vacation down on the beach. But yeah, we used to have people get assigned 3 nights. They would come here from France. It takes them a full day and a half to get over here. And then they'd get clouded out for 3 nights and they would go home with nothing. So this makes it much more efficient for everyone. And it's so much nicer for them too, because they're saving money. So.
And then also just talking about like what our schedule as operators look like. So there are 4 of us on the team as operators. So Lisa and myself, as well as Jessica and Jasmine. And we are observing every single night of the year, 365 days, birthdays, holidays, etc. You name it, the nights are covered.
Yeah.
And so our usual observing schedule looks like 5 nights on. So I am on night 3 of 5. And we're working from, you know, before sunset to just after sunrise. So I was here maybe just about 5 p.m. and I'll probably leave, you know, after 6 in the morning. So long shift, and we're on nights for about 5 nights in a row, and then we'll have about 10 to 15 nights off. During those 10 to 15 days off, we'll, you know, be in the office doing some office work. We have some other projects that we work on. I do a lot of outreach. And so that's kind of how we fill to get to, you know, like on average 80 hours a week, or 80 hours every 2 weeks or so. Yeah.
Yeah. And yeah, I can't add much to that. I mean, that's pretty much our schedule. And when one of us goes on vacation, then we cover, sometimes we'll go to a 5 on 10 off schedule while that person is away. So, and then they just get folded back into the queue, you know, for us once they're back from their vacation. So.
Yeah, I would like to emphasize that remote observers, they work like 12 hours at least in a stretch, and that's a very, very long period of time. So can you both like touch a little bit upon what happens if, for example, the night is not very clear? Say, for example, it's raining, the dome is closed, we cannot observe. What happens? What do you do?
So last night we were closed for the latter half of the night. I'm still monitoring weather conditions. So like, you know, if the skies clear up and we can open up again, you know, I'll be watching for that. But other times, you know, maybe I'll have some other work that I can work on. A lot of the times it's watching movies and TV shows, reading a book, you know, yeah, taking our time. But yeah, we can always fill the night with things that need to get done. Yeah.
Yeah. And we like right now we have somebody coming up who's going to be leaving, who's been here at the observatory for 21 years. And so that would be a good opportunity to go through some of our archive photo books and get those pictures scanned in so that we can put together a little book for her of her years here at CFHT. So that's another little project that we can do when it's cloudy and we can't do anything. So.
Oh, wow. Yeah.
Fun stuff like that, you know.
That's so nice. I love that. Okay. So as we're preparing, as we're waiting for Alexis to do the flats, what other things need to be done before you get ready to get on sky? We know we do weather checks, you're monitoring that. Can't quite do flats yet. Do you do darks? Do you need to do that? Is there like an observing cue that you're looking at that needs to be monitored? Do you use the same instrument the whole night? Also, that thing too. So I'll stop right there about monitoring the queue because I know, we were at Gemini last week and in that session, and of course you can switch back and forth when the weather changes, pretty easy. But oh my gosh, you have certain instruments at the prime focus and others down here at the Naismith. Like how do you do those instrument changes? And when it comes to the queue, are you able to be flexible with the queue, or does it have to be pretty static with just one or two instruments?
Okay, those are great questions. I can just get started on the queue part. So even before beginning the night, there are astronomers at the observatory, and their duties are to actually schedule the nighttime observations. So what we have a software tool where we have all the programs filled in. So all the accepted programs on the telescopes, they have all of their requirements, like the seeing conditions, the cloud conditions. There's how much of brightness can the images tolerate. So there are many such things that go in planning the observations. So we have all of that information in our software tool, and we are basically able to load the different programs and create queues for observations, and hence the name queued service observing. That's because we prepare those queues in advance every day before the night gets started. So as astronomers, we have roles of queue coordinator. I'm an astronomer. I am also the instrument scientist for MegaCam, which is our another imager, but it observes in the near infrared. And what we do is we prepare multiple queues for a given night. So depending upon what kind of weather conditions different programs can tolerate, we have different queues, so that if there are changes in the weather, if the weather worsens over the course of the night, then we are able to switch to observations that can actually tolerate those weather conditions. So generally we have like Q1, that's our main queue that has all the programs that require very crisp conditions. And then there's Q2, which can tolerate a little bit of poor weather. And then generally with MegaCam, we have a snapshots queue where where those programs can tolerate worst conditions. So that's when we are still open, but the weather is not really good. We're not going to get any good data, but it is still open, so we can do all the snapshot programs during that time. So this way, having this flexibility of having multiple queues for one single night, we are able to utilize the time on sky very optimally. And our remote observers are very well trained in how to navigate that, and when they can switch conditions. That is also one of the reasons why they always want to keep a watch on the weather. Slight changes in the weather, it's a continuous watch. Slight changes in the weather, they need to take the decision of moving to moving to a different queue, or like switching back to the main queue, just so that the night keeps going, the data keeps coming, and we don't pause over there. So that's yeah, sorry, Alexis, go ahead.
Oh, so I was going to give an example from last night. So yeah, started in Q1 with some pretty good conditions, and seeing got a little bit worse. It got a little bit softer. And so around that time, I switched to Q2, which is our programs that can handle a little bit softer seeing. And then the seeing got even worse. And so then I did switch to our snapshots queue. And yeah, it's all in the name of that queue service mode, taking observations that can tolerate the conditions that we're currently in. Yeah.
Yeah, and I'm also one of the queue coordinators as well. I work with one of the spectroscopic instruments that we have, spectropolarimeters actually. So I actually can program for the night as well. And one of the things as an RO, if I see in the morning or if I see a projection that, okay, we're going to have high winds from this direction the next night, what I will do is remind our QC, for example, that we can't point into a wind that's too high. We have to point away from it. So please put targets that are going to be like more southerly if the wind is coming from the north, that sort of thing. So we have to also be on top of that and make sure that our astronomers know, hey, make sure you put together a queue, at least one queue that has targets away from the wind so that we can actually get some science that night.
I do also want to talk a little bit about the instrument schedule. Jamaica, you touched on it a little bit earlier, but unlike Gemini, unlike some of the other telescopes, we only have one instrument on at a time. Some of the other telescopes will have a deformable mirror that can like direct the light path to, you know, several instruments or whatever instruments that they need to use. For us, we have scheduled runs. So like for MegaCam right now, you know, I think just starting to, the moon is just starting to wax. But we're in kind of that dark time. So usually MegaCam will be scheduled during like dark times of the month. And then Spiru is usually our instrument. It's actually that one on that
wall there.
On the wall back there. But that's our spectropolar emitter in the IR. And that one can tolerate, you know, a little bit brighter moon. And so that's usually the instrument that we'll have on during like brighter times.
Yeah, so we have blocks of time, and when we get all of the targets from the astronomers, that's when our lead astronomer, Nadine, will go through and she will set up the telescope schedule with all of the instruments so that we can hopefully cover all of the targets that people have asked us to observe. So if there's a particular transit, for example, that we need to observe, we'll make sure that that window has the particular instrument they asked for. So we do have to make sure, or we'll let them know this is the window we were hoping for. Do you have transits in this window? And then they will go and look and schedule their things accordingly. So so we have to work very closely with the PIs, with the principal investigators, so that we know and make sure that we can get their targets for them. So
I see there's a question in the chat.
Mm-hmm.
What other types of jobs are key to your daily operations running smoothly? So I can get started on that. So one of the duties that I was mentioning about with me as the instrument scientist and as an astronomer, so I support one of the parts of my job is to actually support nighttime operations, and that is where my role as a Q coordinator, QC, comes in, where I plan observations for a given night depending upon what kind of programs we have, what kind of priorities we have. So I take all of that into account while scheduling, while making the queues. So that is a part of my job. The other part of my job as an instrument scientist for WIRCAM specifically is as an instrument scientist, I need to do the science planning for that specific instrument during a semester. So we have 2 semesters every year, 6 months long. That's how we operate 365 days of the year with no break. So when we have a 6-month-long semester, the planning for that semester starts well in advance, several months earlier. When we have the proposals coming in for requesting observing time on the telescope, there is a review process that all the proposals go through. The technical reviews are done by internally at CFHT. So whatever proposals, for example, they come in for WIRCAM, all of the proposals the technical reviews for all of those proposals will be done by myself. And similarly, for different instruments, there's MegaCam, there's Spiru, there's Espedons, Sitel, all of the instrument scientists and the people who are familiar with those instruments will be given to do technical reviews for those proposals. There's also the science review part of it. And we have a time allocation committee that works on doing the science reviews for those proposals. Once all of the reviews are done and once there are decisions made on which proposals get time, that is when we have a list of accepted programs and they and all of the PIs, the principal investigators, they start filling in the scheduling part of the observation. So that is when we see all of that on our end, when we want to actually get to scheduling. So as an instrument scientist, I do have to take into account what kind of proposals have come in, what do we have from the review side, and accordingly like make plots and make sure that all the accepted programs are well organized. When there is semester planning, I do have to prepare notes on what are the priorities for a given run, which programs we want to focus on, which programs take the second priority, what do we need to do for calibration. So I make all of those notes. And then the remote observers, they actually review those notes, and we as a team, we do a meeting together to go through all of that, so that everyone is on the same page and what's going to happen for the next 5 to 14 nights. Those are coming in, and everyone is well informed of what's happening. Once we have collected all the data, and once the run is over, for example, if it is WIRCAM, then I will be responsible to do the data reduction. So processing of the data from the telescope. So this is another thing, as all the instrument scientists are responsible for doing the data processing once the data comes in. We process the data, we take a look at it, nothing is looking strange, everything is in place. And then at that point, when we are sure that all the steps have happened correctly, then we distribute that data to the principal investigators. So the astronomers get their data, at which point the astronomers can start doing their data analysis. So that's specifically the role of the instrument scientist. But again, there are different groups. There is software, there is operations. So software people are responsible to work on any kind of IT or software related to things at the headquarters, where we sit in the offices, but also at the summit. If there are things up at the summit, so when something needs to get done at the summit, there are people from the IT and software team that go up to the summit to do this stuff. Operations, that we have an operations group. These are mostly day crew members. They travel all the way from Hilo up to the summit to take care of the telescope. They actually go there very early in the morning. They start their day very, very early. I think about 7 a.m.-ish. So that's very early. So they go up there, they start taking a look at the telescope. Things are looking right. They do a lot of maintenance work. They support all the instrument exchanges on the telescope. The instrument exchanges themselves are also done with the optical engineers on site. So we have engineering team, and there are optical engineers who travel from mostly from Waimea. There are some in Hilo, and they travel up to the summit to work along with the operations people when there is an instrument exchange that needs to be done. So they are the optical engineers are the ones who take care of the instruments which are up at the summit. So that's how we have all the different groups who work together in tandem to make all of the back-end operations ready to go for the night. And we try to make things as smooth as possible for our remote observers.
Yeah, we're like at the end of the whole process.
Yes.
Like,
but that's the beginning of science.
Our software people, our technicians, our engineers, like, we couldn't do what we do without them laying the foundation. Like,
they make us look good.
Exactly. Yeah.
When we get good data, they make us look good.
Yeah.
So.
I love that. Yes, thank you. And could you talk a bit more about the technicians? Because I know like HVAC specialists, electricians, these kinds of skills are absolutely vital to the proper functioning of an observatory. We don't talk about that enough, and I really want to focus on it. So can you talk to us a little bit about those technical positions, those technician kind of positions that are a little bit different than science position, but no less important?
Sure. Yeah.
We have machinists. So if a part breaks, they can actually machine a new part to replace it. We have men who are very good electrically, so they are electrical. They keep our motors running. They string new lines where we need them. They make sure that everything that's powered has power and there enough power from the building to do what we need to do. We have electricians, let's see, machinists. We have engineers who actually make sure that our image quality is good. So the telescope has to be collimated. So when we're taking apart the telescope and reilluminizing and putting it back together, they have to make sure that the telescope is collimated well with our secondary mirror, for example, and with the sky, so that when we're looking out the slit, we're actually getting good images as well. And we have administrators as well. So we have people in our front office who do a lot of typing and whatnot. They write up reports. They help with various things like that.
Travel plans.
Travel plans for people who are coming here who need to work. And we do have French astronomers and Canadian astronomers come here to help with instruments as well sometimes. So if an instrument was built in France, a lot of times the French technician who worked on the instrument might come here to help us understand, like, we have a problem with this instrument, what's going on. And so he'll go up and with the day crew, with our instrument crew, and they will kind of go through and try and figure out what's wrong with the instrument, what we need to do. And so
our software and IT group just finished a cabling project. So they were recabling for the network in the whole HQ building. They are also helping us, with different programs that we use. So we use things like Confluence and Jira, and these are things to help us document things that we can look up, reference things that we need to. They help out with that. So yeah, it's a huge, huge operation. We could not do it alone.
Yeah, absolutely. And, we do keep troubleshooting pages, so to speak. So if something does go wrong during the night and we can fix it, then we will work on it and we'll do it ourselves. And we can actually check things and go, oh, okay. And we can get things working again and continue observing. But then at the end of the night, of course, we have to give our night report. And so we explain what happened, what we did to fix it. And if we had to call somebody, then we actually go into the details of having to call somebody.
It's always a bummer to wake somebody up
at
night.
It's horrible.
Yeah, and I would like to.
Yeah, most of the time, if things go wrong in the first part of the night, we can call somebody early enough. They might be able to go up to the summit, fix it, and get us back on the sky for the last half of the night. So if we save half a night, that's fantastic. Sometimes it happens at 2 or 3 in the morning. And that's when you hate to wake somebody up because they're probably not going to go up until later in the morning to fix it. So we might lose the last few hours of the night. But in that case, we do let them know, hey, there's a problem. And then they will call around and make sure that folks know that we need help at the summit the next day to get things fixed and working. So.
And I'm just about to start flats.
Okay. I was just going to add to what Lisa said, that the night report is a very, very important piece of document. Everyone gets it who is responsible to work for nighttime operations. We as QCs also get it, and what we come to know is what were the night conditions, how was the weather like, how much time we lost, if there was any loss of time, how much time we lost for technical issues, what kind of observations we did. So we refer to that for any kind of specific information for a given night. So that's a very, very important piece of document that the ROs produce right at the end of the night. And before we see the flats, I actually wanted to share this image that I found. So this is an image from the shutdown that we did in October 2025. And the shutdown was, I think, approximately 10 days long, roughly. And that was for, and that was for the reluminization of the mirror. So this is our team of optical engineers. We have software engineers there. We have an astronomer there, and all of them are working very, very hard to get things right and get the mirror back on the telescope. Yeah. That's a very, very
and this actually, what they're doing here, they have an instrument. You see that little arm that's coming out from the center toward us. that is actually measuring where the mirror is on the center. We're trying to center it and make sure it's as centered as we can on its base. So they're measuring that around the outside of the mirror.
Is that a pair of hands coming from the inside?
Yes, yes. There is someone
Okay.
inside the hole.
Okay, I
Yes.
wasn't sure.
Yes.
You can see the reflection as well in the mirror.
Exactly. He's not waving to us. He's actually just, he's waving.
Wow. Okay.
So, yeah.
Incredible. Incredible. This is a great image.
Yeah.
Yeah.
Is.
Where is that person? How are they? How do they get out?
Just enough room. I mean, that's, it's a circle around this, He's pretty skinny too, so.
Wow. Wow. That's something. I love it. I love it. This is great. Is this an image, like an archive image that we can find?
I don't know. Well, a lot of our archived images aren't necessarily available, but I think this might be in the video. We have a video of us
yeah,
doing
I don't
various steps. So
I was trying to find where I have that, and this was the only picture I could get very fast.
yeah.
No worries. That worries is perfect. So if people are any of those who are with us virtually now or watching this recording later, if they have done any kind of astrophotography or imaging themselves, then they should be familiar with flats and darks, but you don't need to do darks, right?
We do. We actually do darks in the morning when we are ending the night. As soon as we do send our done after we've taken our sky flats, it will automatically run through and take darks for us based on the length of a lot of the exposures we've done through the night, especially for the infrared. For the optical, we also get a set of darks done automatically. So they're done automatically at the end of the night when we close up and everything's dark inside.
Oh, that's quite nice. That is automatically done.
Yeah.
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 Sorry, Virgil, go ahead.
Oh yeah, no worries. Okay, so I was actually going to show an image of the MegaCam CCD detector before we actually get to the discussion of flats. So we already have flats coming in slowly, but I think looking at the CCD detector mosaic will be very useful before. Okay, so this is actually the image of the MegaCam CCD detectors. So this is like it's like a panel, and you can see the for a comparison, a 2-cent coin, which is down over here. So there are 40 detectors, CCD detectors, that are together in this picture that makes up the entire field of view of MegaCam. So when we take an image, the image appears in this shape, and you can distinctly see these detectors, these separate detectors when you're looking at any image, any raw image of MegaCam. So the idea behind doing flats, why they are so important, is because they are used as one of the calibration standards. So while fabricating these detectors, they are generally fabricated in the same way, but there are still slight differences when the final product is ready. So there are slight differences from detector to detector, and those are the differences that even though they're very subtle, they can make a big difference when you try to analyze the images that we get when we observe the sky. And the reason we have flats is because we want to correct for any subtleties and subtle differences between the illumination from each illumination between each of the detectors. So when we take a flat image, it's basically we shine the detector with something which is a constant source of light, like a very monochromatic source of light. There is it's almost flat, meaning there are no variations as such from one end of the image to the other end of the image. So when the light falls on the detector and detector gives the response of the detector is recorded. There are actually the variations between detector to detector. They can be tracked. They can be traced. And we want to do that when we want to correct for the actual science images for any illumination differences. So that is the whole point of doing flats. And now I will actually share a flat image. All right, here we go. All right, so that's a raw flat image that we just took a few minutes ago. So there are flats continuously coming in, and they are taken in different filters. Right now, you can see in the panel, which is on the side over here. This is a flat in a calcium HK filter. So that is one of our narrowband filters. And you can see, you can actually make out the different detectors that there are in this image. So all of the response of each of this detector gets recorded, and we can trace what's the response like and correct for that response when we are analyzing the science images. So flats generally look this way. When you're looking at patch of the sky, it's basically any patch of the sky which has equal illumination, meaning we do not want to have any clouds. It should be free of clouds. We also do not want to have any stars because we want to get as plain plane of a sky as we can. So that's the whole point of doing it starting from 18-degree twilight when we can actually start seeing most of that plain sky before we go to the dark time and the stars start popping up.
So in between each of the sky flats, the telescope will move and dither, what we call a dither, if you want to call it that, but we actually move to a different position so that if there are any stars coming into the field toward the end, when it's getting a darker sky, we can actually median filter out those stars and see the pixel-to-pixel variations to get rid of them. So, and actually the other thing that the Viraja didn't mention is it takes time to read out these CCDs because these are rather large. And so each of our CCDs themselves have 2 amps that we're using to read out. So you'll see that each one has 2 different panels on it. And that the kind of basic wavelength or the basic brightness of each one depends on that readout amp as well. So we're also correcting for the response of that readout amplifier.
Yes, so every CCD detector, every CCD has 2 amplifiers. That's how it's set up.
And that was to cut down on the length of time it took to read out the CCD too. So otherwise, right now it's, I think, about 41 seconds to read it out. And so that's a lot of overhead when you're doing, a 1 minute exposure, then it takes 41 seconds to read it out. It's a lot of overhead. So the longer your exposures are, the more efficient you are at actually taking images.
Yeah, so the overhead time, that's a very, very important factor, and sometimes a very subtle one too, that if you do not take that into account when you're doing your exposure time calculations while designing the proposal, then it can make a very big difference in time because we generally don't want to have just a single image. We want to have multiple images in different filters, depending upon how big of a sky you're trying to observe. So 40 seconds per exposure time, even if we have 100 exposures, it just shoots up. So that's the reason, take into account that overhead time of 40 seconds while doing the exposure time calculations while designing the proposal. That's very important. And it's 40 seconds for MegaCam. The overhead time is different for a different instrument. So if we have Spiru on Sky, then that overhead time is going to be different. For VirCam, the readout time is very, very short. And that is one of the reasons the observers have a very tough time trying to handle VirCam observations.
Yeah, we get we have someone who had a program who was doing parallax. So he was essentially observing stuff on one side of our orbit and of the Earth's orbit around the sun, and then from the other side of our orbit around the sun. And he was looking at the same areas of the sky to see how much the star moved to calculate the distance to those stars. And he has long sets, like 36 5-second images in a row. And if we're not on top of it, we can get very behind in our grading, because we have to grade each image as it comes off, each spectrum that comes off. We are actually grading it and giving a comment so that the people know what was happening when we were observing.
And really schedule those bathroom breaks.
Yes. So we wait for the 1-minute exposures in the infrared so that we can run to the bathroom real quick.
I love it. Now that's what I'm talking about. That's planning right there. That is a plan.
Yeah. Yeah, so generally for WordCam, it can get pretty bad. Siddell is, on the contrary, very nice in that sense.
Yeah.
Yeah, because Siddell generally has very large observation blocks. So once you like set an observation, it can go on straight for 2 hours, and you can actually get to doing some other stuff and not worry about what's happening. Yes.
Okay, let's see. We have some questions here.
Yeah, I noticed that somebody asked a question about who can ask for telescope time here.
Yeah.
Unfortunately, we're a little restricted in that sense, because anybody who's at a University of Hawaii university can ask for time. Any astronomer here in Hawaii, any astronomer in Canada can ask for time, and any astronomer in France can ask for time. Most of our money is coming from the equivalent NSFs of Canada and France, and then all of the money through UH is coming to us from NSF as well. And so those are our partners, so to speak, in the observatory. We also have a Korean group that actually helped us with an instrument, and they have had time on our telescope, as well as the Taiwanese and the Chinese. They all have had time. And actually, we also had, for a short time, Brazilian access as well, because they were helping with some other things that we were doing with an instrument. So we have had other partners that have come in, given money or given expertise to help with things, and then we've given them time, so much time. And our board has to okay that. But if you want to ask for time on our telescope, you got to be collaborating with someone who has access to our telescope. So
I was going to get to that. I was going to get to that. So one way is either being at a Canadian-French UH institute, or being in one of our partner agency institutes. But the other way is work in collaborations. We live in a collaborative world right now. So if someone is working in collaborations with people who are in Canada or France or UH, then that is one other way of getting data. And we have, I mean, there are many examples. So we do have a lot of principal investigators whose teams are pretty huge, and they are working with people, not necessarily that they have a direct access to CFHT, but they do have access because they are on those collaborations. So that's one other way.
That's great. Thank you for explaining that, because I'm just chatting here with some of our participants, and Julius was saying that they'd applied for telescope time, but hadn't like gotten it. And
Yeah.
and so I was just curious because of course the US has the open sky policy, but of course you're working with another country, so I wasn't sure how that would impact people's ability to apply for a time. Okay, so
Yeah.
we pair with someone who has access. Yes, like someone from France or Canada. That's how we're going to do that. Okay, I like it. I like it.
Yeah, yeah. Yeah, and I would also like to mention actually, so we also do Maunakea Scholars programs, and that is one that's like a subset of our users. So Maunakea Scholars is an educational outreach program that happens on all the Hawaiian Islands, and we at CFHT also have time. Especially on MegaCam, sometimes on our other instruments like Espidons. And we actually do observations for high school student projects. So these are students who are working through science subjects in the school, and they express interest in doing observations with the telescope. So they have they have like a lot of guidance from their teachers. They have guidance from a Mauna Kea Scholars team. That's like a core team that works with all the different observatories together. So they work with both of them, and the students come up with interesting projects. They want to observe some object that is of interest to them, and they put a very short proposal, like a page proposal, with what's their idea and why they want to observe such a target. We do review for all of those proposals as well. It's not like a thorough review, but we do look into how much efforts the students have put in to investigate, to research, and come up with target names. And we actually, for some of those proposals, we actually grant time on the telescope. So at CFHT, especially with MegaCam, we do a lot of Mauna Kea Scholars programs as well. So we get data to the high school students, and they always have positive comments on their experience. So I think that's one other group of people for whom we also actually collect data.
Speaking of data, Viraj, I don't know if you're going to go over this later, but like being able to get some of our data from CADC.
Yeah.
Okay,
Yeah,
sure.
we do
Yes.
have an archive as well, that all of our images are stored, all of our images and spectra are all stored there, and you can request access to that archive and go in there and just do some data mining after the proprietary period for the astronomers who actually ask for the specific data. So
Yes,
Yeah.
so we'll give the astronomers their data, and it's proprietary for about a year, so that's so they can, write their papers, make their analyses, things like that. But after that, all of our data is free and open to the public. So you can go to the CADC and download, data from any of our instruments for years and years and years in the past. Yeah.
Yeah, so CADC is the Canadian Astronomy Data Center. It's basically a center where all of the data from many different observatories is hosted, and Canada-France-Hawai'i Telescope is one of those several observatories. So CADC is their actual center lives in. Oh, great. Okay. So their actual center lives in Canada, in Victoria, in British Columbia, which is on the Pacific coast. So that is where all of the data, once it crosses the proprietary period, which is a year and 1 month precisely, that is after which the data is available to anyone. So anyone can go on the website, they can do data mining, they can search for a specific object, and they can download the data for that specific object and do their own analysis. So that is also one way. And generally with archive data, there's usually a lot of data in the archive. Some of the data has not been used even once, and our archives are generally very good sources where yes, you can find a lot of data.
Yes. So let's say someone wants to use some of this archived data. So here we are. When I click on CFHT right here with the raw data and data processed at CFHT.
Yeah, sure. If I can share my screen and I can
Yes,
like navigate
please.
through the process. Sure.
Yes, take us through the process. And then I'd love to come back and see what's going on with Lisa and Alexis and maybe even get a quick peek at some spectra or something. I know Ju Julius mentioned being excited to see some spectra.
Sure. Okay. So let me share my screen.
Yes, please.
All right. Okay. So that is the CADC website. You can see their data from many different telescopes. So JWST, there are space telescopes as well, not just ground-based observatories. So that is something to also specifically think about. So there's JWST, Gemini, CFHT, JCMT. These are all Maunakea observatories. Hubble Space Telescope, that's a space observatory. These are again ground-based observatories. NeoSat, that's the satellite. So there are many observatories of the data that you can utilize. There is a list of some advanced data products. So these are the ones that probably also have reduced data. So you can see, you can find for CFHT, this is a Canada-France-Hawai'i telescope legacy survey. So this was like a 5-year long survey that happened, I think about 20 years ago with CFHT. So this is another data mine that you want to like dig into and look for images. These have really beautiful images. Okay, so if you do want to search for specific objects, we need to go to advanced search. We can enter name of a target. Let me enter M31. So M31 is Andromeda Galaxy, which is our neighboring galaxy, and it's a very well studied galaxy in general. We do have a lot of images of Andromeda with MegaCam, and I'll actually share some of the science that we do with MegaCam a little later. But we have M31, so we have selected the target. We can go down and we can do our specific selection for CFHT. We want to have mega prime. And let's just say we are observing it in G. So that's the G band filter, meaning that the image that we observe, it will be taken in green light, in the green band filter. So let's say G, and let's do a search. We have to be a little patient. I don't know what the search is going to give us. So that's always a mystery.
Yes. Is Mega Prime the same as Mega Cam?
Mega Prime is same as MegaCam. Lisa can probably tell you a little bit about the history of it.
There's a
But
very
yeah.
subtle difference, right?
Not really.
Okay.
It's the same instrument. It's just that a lot of people we started out using Mega Prime as the name of the instrument. MegaCam is actually the camera of the instrument, but everybody calls it MegaCam, and we log in as MegaCam, and it's like, yeah, but it's actually Mega Prime. So but that's just
Subtle.
very subtle difference there.
Yeah, it's
For clarifying.
technology. In like as of today, both of those are used interchangeably for the instrument. So yeah, it's just MegaCam now.
Wow.
All right.
Okay, I thought that was a new instrument. Like, wow.
No, it's the same one.
It's the same one. Okay, love it.
Well, that's nice. You can see the nucleus very well
So
there.
this is one image that I just clicked on. So this is a preview of the raw image. That's the Andromeda Galaxy, the center. So in this case, we are actually looking at invert color image. And what that means is all the bright pixels that are on the CCD, all of those are in black, and all the so the more the more black the pixels are, the more bright those pixels are. If there is fainter, so all the background that you see, that's all faint, which is all the background. So there is very low pixel count levels in the background. So the central blob that you see, that's sort of indicating that's where the bulge of the galaxy is. And then it's very, very faint, but you can see like very faint light around the galaxy, around the central blob. And that is where the disk of the galaxy is. So it's in a very specific orientation. Let me pull up another image if it looks any different. These look pretty much the same. It's the central blob that we can see very clearly. Let me go to the actual image, the full processed one. I think this one has yeah. So this is like a full
Oh,
processed image of Andromeda.
yeah. Wow.
And this is actually called a composite image. So it's not just in one filter, not just the G filter, but there are different filters. So the image was probably taken in the red filter, in the blue filter, in the green filter, and all of those images were carefully combined to form a color composite. And so what we're looking at is the final image where all the different colored images, they were carefully laid on top of each other, aligning the pixels and the coordinates properly. And that is how we get a composite image. So in this case, we are actually seeing what I would call that is this as an optical image of Andromeda galaxy. This is the central blob. So when we were seeing that very dark blob in black pixels, that was pointing towards the center of the galaxy, and then the fuzzy structure around that blob is where the disk is. So if you look at this picture, that is pointing towards the center. So this is the center of the galaxy where we have the supermassive black hole, the very, very massive object. The disk of the galaxy is where we can actually see darker lines. So this is all the dust in the galaxy, which does not emit in the visible colors. And because it does not emit, all of those appear like dark patches in the disk. But you can see all the stars, they all emit in optical colors, and you can see all of them as very, very bright objects.
That is incredible. And so these archival, well, not just the archival images, but the data in general can be used for anyone. And let's say we want to look at are these FITS files? I'm sorry, let me go back. I can't see. What kind of, yes,
Yes.
FITS files.
Yes,
So we could use those FITS files for anything if they're wanting to do their own research, go back through old data, and they could still use this data even though it was someone else's. Now it's non-proprietary, and they would use it, cite, and is there directions on how to properly cite observations if you're using someone else's here on your in the directions here?
That's a great question. So you can see when you enter a specific criteria, you get all the list of everything that's available in the archive. There is a download option that you can click, so you can select multiple images and click download. You can get all of this as a CSV table, as a VO table. So there are different forms in which you can download the data, and you can view those files in any piece of software that actually gives you that you can use to visualize FITS images. So that's the first part of it. About the citation, I will have to dig a little bit into how to pull up the citation. So let me go back to the website and let me pull up the citation page. Till then, Alexis, can you tell us what's happening in the control room?
Yes, so I just finished a set of flats in two filters, the CAHK, and we have a new filter, M4376. So just trying to get as many flats as we can in those new filters. I just finished a sequence yesterday. But now that that's done, we have a little bit of time before the start of 12 degree. I'm getting a focus sequence on one of those newer filters as requested by our engineers. So yeah, we'll be doing that very shortly.
So one of the things that while she's looking for that, one of the things you need to know is in order to go from the images that we get off the telescope, the problem is you cannot put CCD butted up against each other. And so there are little spaces in between all of these CCDs in our array. And so in order to get a picture like that, you actually need to dither. So you need to dither around a little bit and then fill in those little spaces in order to get your final images that don't have those little gaps in between. And so that's what we do as well. We make sure that our dithering pattern is working during the night when we're taking those dither patterns and putting together larger images. So we have to be very careful and watch that too. And sometimes, an offset will fail and then we'll have to restart it and try and get it to go to the right space. So, but that's another thing that we have to be aware of when we're using this instrument in particular, to make sure that the dither pattern is working.
So what happens if the dither pattern is off a little bit? I mean, because it's supposed to be just slight changes in movements to capture.
There's subtle differences there. Some of them do larger dithers, some of them do smaller dithers. So it varies depending upon the object that they're looking at. And for a lot of these really nice pictures that we do like this for our calendar, we actually have a smaller dither pattern. And so it's going just far enough so that it's actually moving to fill in just those little gaps. For other people who are actually doing larger images, they might want to dither in a larger space just to get a larger area and a larger picture. But it does vary a little bit. And we do have some predefined dither patterns that they can choose from in our system so that they can actually go in and decide how big a dither do they want to use. So those are all pre-programmed as well.
Oh, I see. And so when we're thinking about Lisa, the what I love that I have this incredible privilege of working with astronomers from so many different observatories. Are there astronomers or staff in general assigned to support specific instruments besides astronomers? Like, because I know Vera just said that she supports a certain instrument, but do you all as well too? And if so, because I think you said you did WeirCam or is it Spiro?
She does WeirCam.
I do WeirCam. I also do scheduling for MegaCam, but I'm the instrument scientist for WeirCam. So I take care of many things with WeirCam, but I'm also a scheduler for MegaCam. So which means I can schedule MegaCam observations as well.
And we do also have some engineers assigned to certain instruments as well.
Yeah.
Yes.
So we always have at least one software person, one engineer, and one astronomer all assigned to that instrument. So if there's something at the beginning of the night that isn't quite working, we know who to call usually if we need help. The other thing is that because I have been here a long time and I've seen all these instruments, we have to learn all of how to observe with all of 5 of our instruments that we currently have. So we use each of those instruments. Some of them we don't see as often as others because they don't get scheduled as often. But I am also a Q coordinator for our Espidons, which is Espidons instrument, which is our optical spectropolarimeter. And so if by chance there are a bunch of people gone in the summertime, gone to a conference or whatnot, I'm still here. I'm probably able to actually schedule a few nights in a row and put together all the cues for the person who's going to be observing that night.
Lisa is an incredible fount of knowledge, and very often I'll be calling her like, Lisa, please help me.
I love it. And that's it. And that kind of camaraderie, that teamwork, that support, that
Yeah.
I love it. And that's what also keeps, besides coffee and all those other things, it keeps you going too.
That little bit of chocolate you need at 3 a.m. to keep
You
going,
do.
you know,
You got it.
things like that. Yeah.
But support from actual humans
Yeah.
is super
Yeah.
incredible.
Absolutely.
Can we talk a little bit more about this new filter?
Oh,
Yes, so we have a couple new filters for MegaCam. And so like in this process, we're, implementing them, taking some observations with them, but because they're new, we want to get a lot of really good flats. We want to get a lot of really good focus sequences, so that we know kind of what we're looking for later on down the line. Yeah.
yeah, because all of our filters are programmed so that when we switch from one filter to the next, the focus offset automatically goes to that next filter. And so we need enough focuses to actually get the central best focus so that it will automatically go to where we need it to go to be in focus. So
This is kind of like a general procedure whenever any observatory would get new filters or they will get new instrument, they will have specific nights scheduled for using that instrument or using those filters so that we understand in general the behavior, the specifics, the technicalities, the practical differences for using those filters or those new instruments. So we generally have that, and it's true for any observatory.
So MegaCam is like the most used instrument there. Why now are there new filters? Is this to extend the capabilities to make the images, crisper, better image quality, all of those things?
many different reasons.
Yeah, I would say, more so like extending the capabilities of what,
Yeah.
what wavelengths we can observe
Yeah.
with MegaCam.
Yeah, a lot of time. Well, this is one of the few telescopes in the world that is actually quite reasonable in the ultraviolet band. And so a lot of people, our big legacy survey, a lot of that was done in the U band, in the blue. And so when people need U images, they will come to look at our archive because we've got some of the best images in the U. So because of our U sensitivity, we actually do have some of the best images in the U. And we that doesn't mean we don't go into the IR. We try to go we have R and I, we have filters that far out, but sometimes an astronomer will want a specific band pass that's not a standard band pass. And so they will send us these special filters, and then we will actually get them calibrated and use those because they're looking at a specific wavelength range for specific objects at a certain distance from us.
Okay. Okay. Thank you for clarifying that. That
Sure.
totally
Yeah.
makes sense.
Yeah.
Ooh. Oh, Virja,
right.
what are we looking at here?
So I was just going to show where to find the proper citations for using CFHT data and for publications. So this is the homepage of CFHT. And from here, if we go to science in the top navigation, and if we look at the left navigation all the way to the second last option, publications, so that is what we have. So there are some instructions, and then there is proper acknowledgement for CFHT papers. If they're either using CFHT data, they're either using any of the CFHT software capabilities, or even if it is legacy survey data, then this is the proper citation. So and the citation is slightly different for different instruments. So do pay attention to what kind of data you're using. If there is MegaCam, there's a standard version, the shorter version as well. There's a WIRCam, Espedance, Citel, and Spiral. I think the MegaCam is just, it just appears to be twice, but it's basically the same thing. So if we go like down here, it shows the MegaCam acknowledgement, any of the related publications. So yeah. This is a standard version. This is a shorter version. So
Oh, I see.
yeah, depending upon whichever fits in the paper requirements. So
Oh,
yeah,
this is very helpful.
Yeah.
Yes. Thank you so much, Virgil. Yeah, I'll make
No
sure to.
problem. There's also, so here's also a scientific publication list. Oh, I was hoping it would take us to some list. I think there is also a list of publications when many of the recent publications of CFHT. I'll try to find that. If I do find it, I'll share back again.
Okay, thank you. That'd be great. And I'll include that in any in our follow-up emails with the survey. I'll add the all of these links that we looked at today to that. Yes. So when you were showing the image of the Andromeda galaxy, like that was just so incredible. The color image, and we could see I think there's M8 right there as well. And I forget the other one. What's the other galaxy there?
And
Oh
see
my
something.
God, I can't remember the name on top of my head.
You see something. Yeah.
We're gonna go with that, Lisa. Mhm. What she said.
Anyway.
That's that because that is correct. It's something like that.
Yeah.
Just the clarity, the colors, and this is we come back to those filters, that are used. How is it that you're able to make those seamlessly come together? Because you have separate color filters, but by the time we look at these images, especially the ones that are in the calendar, and I have like a dozen CFHT calendars, they're incredible. It just it's hard to imagine that it just seems like that's exactly how it came together. But that's a lot of work that you all do, and you were saying that that is part of what you work on. So is that training a part of kind of what you learned to do at CFHT, or does this go back to some kind of foundational skills that you had when you were at university?
Yeah, so this is where the data processing comes in picture. When we get data, raw data from the telescope, it's not as is, it is not useful for science. We have to make it useful for science, and that goes through extensive number of steps till we get to that kind of image that can be used for science. So the entire part of data processing is once we get the raw data, we need to correct the data. So if we have to do the bias subtraction, we have to do the dark correction, the dark noise correction. We have to do the flat fielding. That is where we use the flat calibration images. There's also a point where we need to like stitch the CCD images. That's not an absolutely required step if we are only looking at one particular object, which is in one particular CCD, then we need not worry about all the other CCDs. So we only take into account that CCD and we process that specific image section. But if you do want to have like a full image stitched together, then we'd have to actually stitch the CCD images together, which means we have to align those pixels properly together. That is something that the software tools that do the data processing are able to do. Once the images are stitched, we need to also do a flux calibration. And depending upon whether we want an absolute flux calibration or a relative flux calibration. So that is why the standard star observations are useful. I don't know, Alexis, if we have already begun standard star observations.
Almost. So we're almost done with this focus sequence. We have started, I mean, it is a little bit past 12-degree twilight.
Okay.
So yeah, this will just go to, engineering time. But we're almost ready to start, I'd say in a couple minutes.
Okay, so once we start the standard star observations, we can take a look at some of those as well. But standard star observations are basically the calibration stars, so that and what we measure is we know the light coming out of those specific stars, and we use that light to calibrate the actual images. So that is why the standard stars are useful for. So there is a flux calibration step that happens. And after that point, that is when the image itself is ready in a specific filter, but there can be several images in the same filter, and these can be dithered images. As Lisa mentioned earlier, they can be at slightly different positions. So the goal is to align those dithered images together. And that is done when we have a pixel to coordinate mapping. And that is how we can precisely lay one image, and then the dithered image we can shift and lay it on top of it. So that is how that's done. So there are software tools that take care of that process as well. So once the dithered images are aligned according to the correction, the pixel to coordinate mapping, at that stage they can be median combined. And then the combined image together basically is very useful because that boosts the signal noise of the entire image, and you can see things much clearly. So that is why those dithered images are also, that's one of the reasons from a science perspective why those dithered images are also very, very useful, because they just give you at the end a boost in the signal noise. So once you have a dithered image and a combined image in one specific filter, and you have multiple images that way in different filters, that is when the point comes when you have to align the different color images together to form a composite image, as we saw for the Andromeda galaxy, the final galaxy image. So that is when in different colors, there is a specific tool when you're using astronomical software tools. There is a specific tool that will allow you to lay different colored images on top of each other and try to align the different colored images such that you are actually laying the proper coordinates on top of each other. So if the color correction is not correct, you will actually see extended blobs in as you'll see the stars, which should appear as point sources, but they will appear as extended blobs with some kind of chromatic aberration happening, some weird features that you can pick out very easily with your eye. So for such a beautiful image to come together, the point where we do a composite image, that step should happen absolutely correctly. So yeah, and that is how we get such a beautiful image that we see for Andromeda.
So we just started the first standard image. So
Okay.
it'll be done in about 2 minutes, 2-3 minutes.
Okay. Till then, I'll actually share another image, which I personally like very much. So this is an image. This is also a composite image, and you can see most of the sources in this image. They are galaxies. Some of them are stars, which you can pretty easily make out when you see these very dark white blobs. These are the foreground stars. So you actually see them very bright. But most of these are all galaxies. And in this case, we were trying to map a very big patch of sky. And this is called a low surface brightness mode for MegaCam specifically. So what we try to do in this low surface brightness mode is we try to get many exposures together in a certain patch of the sky. And we want to really highlight the diffuse features in the image. And you can see there is some diffuse gas emission right over here. And this low surface brightness mode really allows for that enhancement of the diffused light. So this is a very special mode that we can enable with MegaCam. And when there are lots of studies on diffuse emission, that is when we make use of that mode. So this is again a composite image. The processing is mostly done in the way that I described. But again, this is used for a very different kind of science versus looking at a very like a specific individual galaxy.
So this is incredible. And I love this, and having done sessions with you before, of course, which you brought this out. And this is the first time I think you said that it was your favorite. I kind of guessed it. But thanks for clarifying. I mean, it's it's stunning, but it reminds me so much of a painting, and in particular, Starry Nights by Van Gogh. It looks so much that the kind of the haziness, the wispiness that's in there. And you said this is used for a certain kind of science. When would this low surface brightness mode be used?
So this is when we are looking at the emission in between stars and in the interstellar medium and the intergalactic medium. So this is all the diffuse emission that comes from different gases. So when we have there is hydrogen gas. There is some of the light that we see is because of the oxygen. There is some emission from the nitrogen gas. So this is basically trying to understand the composition and the interaction of different gases in this medium. And this is when we are studying this, because all of this emission is in the background. It's not actually studying the objects, it's studying the background. And that is the reason when we are studying either low surface brightness galaxies or we are looking at very diffuse emission, this is when this kind of observing mode, the low surface brightness mode is very useful.
Ah, okay. And so this was partially part of Julius's question here was that these are these images actually useful for science, or is it just more of a way of taking beautiful, beautiful pictures, right? No. Okay. So this is good to know. This is good to know. And so also a little follow-up there. He says that he's getting concerned about the CCD moving, but doesn't remember exactly how you explained it earlier. Can you take us back through that as we have about 8 minutes left with you guys?
Sure. Okay. So which part exactly do you want me to go through again?
I mean, he said he's getting concerned about the CCD moving, but he can't remember how you explained that earlier.
I
But
mean, the small dithering patterns, you mean? I
yes,
mean, we actually moved the telescope around this specific image that we're looking at. So we're actually doing very small shifts right around that target so that we can fill in those holes in between the CCDs. So we're not moving the CCDs, we're just moving the telescope and doing more imaging.
Yes, yes. So it's just the wherever the telescope is pointing, that pointing moves slightly. So there's actually the telescope that is actually moving and taking images in at different positions. So nothing happens to the instrument itself. It's stable. It's up there. No one is doing anything with that. It's just the telescope which is pointing in different parts of the sky, but very, very close parts of the sky. So yeah, that's the difference.
perfect, thank you. And that's exactly also what Rob said in the chat here. That's probably referring to dithering. Thank you, Rob, and thank you, ladies. Julius, if you have a follow-up to that, please let us know. Just drop that in the chat for us. So what do we expect for the rest of the evening, Alexis? Because you'll be getting to some of your science imaging soon.
Yes. So we're doing some standard stars right now. Once we get to that 12 degree, 18 degree, we'll be doing some of those like larger programs. So these are programs that are looking at objects over more than the course of one semester. And so rather than having them reapply every 6 months, we do what's called our large programs, and like they'll apply once and then it's, for like multiple semesters, maybe a couple of years. And so we're doing a lot of that tonight. We have some snapshots later in the night to fill some time, and we might have some targeted opportunities as well. So those are special projects where, they might not know specifically like where or when this certain phenomenon is going to show up. But they'll give us some like they'll let us know ahead of time, maybe like days, weeks before. And so we'll hopefully get some of those tonight if we stay open all night.
Yeah, sometimes things are found in the X-ray or the or gamma rays, for example, and the error boxes for those targets are usually quite big. And because we have a 1 square degree field here, they will ask us to do follow-up to see if we can see it in the optical and identify what exactly that target is in that field. So we are helping them to identify what that phenomena is. Also, we have quite a few target opportunities from the University of Hawaii. They're actually following asteroids that are found in the Pan-STARRS telescope. So we're helping to plot the orbits for a lot of these asteroids that they're finding. Near Earth asteroids as well as other further out. So
Oh, that's so fun. Yes, yes. Okay. So when you're this kind of work, and especially this long-term one, the characterization of the orbits of the near Earth asteroids and things like that, this is from UH, for example. Are there students also working on these projects? Because I assume these are kind of put in by the professors as the main PI, but do students get opportunities to collaborate with their professors and using CFHT data?
Yeah,
Okay.
yeah,
absolutely. Yeah.
Good.
The
Yeah, we
PIs
have
pretty large teams. Yeah.
Yeah, and we do have the other biggie over at UH is comets. We have somebody who keeps watching a lot of these comets that are coming in, and they're trying to determine when are they going to start, sending out and melting, and showing a little bit of a tail or maybe an ion tail, whatnot. But so we have, and they have, all of these professors have students who are working with them to actually analyze a lot of these things and measure various things.
Remember correctly, so Pan-STARRS is at UH, and Pan-STARRS does like large survey, like swaths of sky every night, just trying to like find these potential candidates. And when they do, they send it to us to be like, hey, can you follow up on these candidates to see what,
And some of these targets are actually 22nd magnitude, 23rd magnitude. So we're doing like 2-minute exposures or 5-minute exposures for some of the fainter ones to really find them. And we're actually using non-sidereal tracking, which means we're actually tracking the asteroid, and all of the stars are going to be trailed in the image so that they can easily find that one target that isn't moving. So.
Yes, yes. And sometimes it's a confirmation of the detection of a comet or asteroid, and sometimes it's actually they already know that that's the object and they want to actually measure the orbit. So it depends upon the science goals. There are different science goals, but yeah, for the moving targets, it's either the asteroids or the comets. And I would actually like to share the standard star image, which has a satellite streak.
That figures.
Probably not surprising, but yeah, okay, we do often see satellite streaks in our images. And Lisa was mentioning earlier about they putting comments in, so they put comments for every single image. And this is one of the things that definitely goes into the comment if the image has satellite streaks on it. But this is a standard star image, so we are basically looking at a patch of sky where we are looking at a specific standard star, but then there are many stars in the full image. And it's usually helpful if the satellite streak is not running right through the center of the image, because typically the object is at the center of the image. But if it is going through the center of the image, they take multiple exposures so that they can use different images and not just rely on a single image.
So is this not going to be usable because of the satellite streak through it?
I think this image should be usable. I'm not exactly sure where the standard star is, but I think I would imagine it's somewhere in the center of the image. The satellite streak it appears like it's kind of like a little bit on the side, so I think this image should still be usable. But yeah, if it is like running right through the center, then it's generally a concern. And it depends. I mean, if there are stars, or if they're trying to image the entire field, not just a single object, then many of the satellite streaks can be an issue, and in some cases they would have to just discard the image, and it will not be useful at all. So those are sad situations.
Yes. Do you find that you're having more satellite streaks show up in some, yes, yes, okay, okay.
That's a big nod that I see.
It's a
No,
little
no.
frustrating.
It's
The
a
more
little-
satellites people are sending up, the more
Yeah.
contaminated our images get.
Yeah.
So we're definitely seeing an increase over the last,
Yeah.
10 years or so.
Yeah, and I had never seen an image with 5 trails in it until they started sending up all these constellations, satellite constellations, and now occasionally we get up to 5 in our 1 degree square field. That is, it's crazy, It's we don't like that. We don't
Frustrating.
So
Yeah. I can imagine that creates possibly more work for your team who are doing some of the data reduction and you gotta pull those out or something.
It's definitely
Yeah,
harder work for the data processing for sure.
Yeah. With satellite streaks, it's not possible. I mean, there's no straightforward way of getting rid of satellite streaks.
Oh.
There has to be very extensive processing, and it's So generally, what would happen if there's not a lot of if it's not absolutely necessary, some of the times they just discard the images and not bother about them. But yeah, I mean, removing satellite streaks is it's a very, very tedious process.
So these first 3
Definitely don't want
standard
them.
stars, all 3 of them have satellite streaks in them.
Oh
What?
my God, there you go.
Just to prove our point. Wow. So are you gonna take some more, Alexis?
Probably not for these standard stars. And then, yeah, depending on where they are in the image,
Right.
like if it goes right through what I expect, like our target is, then maybe I will.
repeat.
But if they're kind of like on the edges, something that could relatively easily be processed out, then I probably won't.